This lecture is the third part in a series that discusses the properties of the DTFT. In this lecture, we will talk about differentiation in frequency, Parseval's identity, and convolution, and we will also discuss some examples. Let's start by the differentiation in frequency. So the property says that the DTFT of the signal nxn is j times the derivative of x of ej omega by d omega. So this means that if you multiply the signal xn by nxn, then this is how you can obtain the DTFT. Usually this property is useful in finding the inverse transform. So basically you notice that what you have here is the derivative of something, and the way you would go back to find the signal is by applying this property. And I think in the last lecture in this chapter we will use this property. Now the proof follows immediately from the definition, and if you take the derivative of x of ej omega with respect to omega, so you get the derivative of the sum is the sum of the derivatives, and the derivative of e minus j omega n, again the derivative is with respect to omega, so this is going to be equal to minus j n e minus j omega. So you have here minus j and n e minus j omega, and then this would be equal to minus j the DTFT of nxn. Again, this property is useful when going in the other way. So you would try to, when you're trying to invert you're going from the Fourier to the time domain, you can notice that what you're dealing with is the derivative of something. So it's the signal is nxn. That would be the corresponding signal in the time domain. Parseval's relation or Parseval's identity is a famous identity that characterizes the energy in the time domain, which is this part here. So this is the energy of the signal in the time domain, and this is the energy of the signal in the frequency domain. So it says that the energy of the signal in the time domain, it says basically that the Fourier transform or the DTFT kind of conserves the energy. You can find the energy either in the time domain or in the frequency domain, and you would get the same result. And this is a famous identity, and there's a nice example on how to use it in the book. So you can do the example 5.10 in the book as try it yourself exercise. Now we get to basically one of the most important properties of any Fourier transform, is that the output of a system, which is the convolution, so basically the convolution in the time domain is multiplication in the frequency domain. So, and usually this is useful when studying the input-output of an LTI system. So if x of n is the input of an LTI system with impulse response h of n, then in the frequency domain, so here in the time domain, the output y of n is obtained by convolving the input and the input, and in the frequency domain, so the signal has the following DTFT, and this is the frequency response of the system, and the output is y of ej omega, and then we have that y of ej omega is equal to x of ej omega times h of ej omega. So basically multiplication in the time domain, or convolution in the time domain, is multiplication in the frequency domain. And the importance of this property is that because convolution is very tightly connected to the input-output of a linear time invariant system. And we will see this, we'll apply this a lot in examples. So let's apply the convolution property. So by doing the following problem. So suppose that we have an LTI system or LTI filter with the following impulse response. h of n is 1 over pi n sine of pi of 4n. And the question is, what is the output of this filter to the following inputs? Here I have x of n is a n u n, so this is a complex, an exponential, or x of n is sine pi by 2n plus cosine pi by 8n and sine pi by 6n by n. Now, to be able to find the output, first we need to find the, it's easy here to go through do things in the frequency domain and then come back to the time domain. Now, to go to the frequency domain, so basically our roadmap is going to be like this. So first we're going to find h of ej omega, and then find y of ej omega equal to h of ej omega times x of ej omega. And this is the input. And then once we have a y of ej omega, we can find y of n. So the first step is to find y of ej omega. And I don't know if you remember, is that this function that looks like the sinc function. So this, if you remember, this corresponds to, in the frequency domain, to a box or rectangular function that is repeated, and it's basically a low pass filter. So here I have the inverse DTFT or the DTFT of the impulse response. So if h of n is 1 over pi n sine of pi by 4n, then the DTFT of it is the low pass filter with cutoff frequency here pi by 4. So omega 0 is pi by 4. So let me write it down here. And again, it's repeated. So this is what's happening in the interval minus pi plus pi, and then you get the same thing repeated because the DTFT has a frequency equal to 2 pi. Now, if you don't remember where we got this from, we did it in one of the previous lectures. Basically, we proved this, or well, I've given it to you as a problem to do yourself. But if you don't remember, you can. So you can just apply the definitions to get this. So again, so the interesting thing is that you will get a low pass frequency because you're allowing in at the output. So when you multiply the frequency, so suppose I have I don't know. So the input. Let me draw the input in blue or in red. So let's suppose this is H omega, and you know that the output y of ej omega is the input. The frequency spectrum of the input times h of ej omega. So let's suppose that x of ej omega looks something like this. So in the interval minus pi plus pi, maybe, I don't know, let's suppose it looks something like this, and it's going to be repeated because of the periodicity. Then you know that since these two things are going to be multiplied to give the input, so everything in the signal that is between minus pi and minus pi by 4 in this interval here, this signal is going to be multiplied by 0, so it's going to be zeroed out, and what remains is what I'm going to highlight in green. So what remains is this part here of the signal. So only the low frequencies of the signal are gonna survive, and then it's gonna get zeroed out here. So I don't know if you can see the green signal. Again, it's repeated here, so this part is gonna survive. Only the low pass frequencies are gonna survive, and this is why this is a low pass filter. Now that we have the frequency response of the filter, we can find the output for each one of these cases. So let's start with the first case. In the first case, the input is an u of n, and we've done this before in this case because the magnitude of a is less than 1, then x of ej omega is 1 divided by 1 minus a e minus j omega, and so I can get the frequency of, or y of ej omega of the output. So it's going to be x of ej omega times y of ej omega. So like I said, what you're going to pick up, so you're going to pick up whatever is in the interval between pi of 4 and minus pi of 4 and plus pi of 4, and it's going to be 0 otherwise. So this is what's going on in the interval negative pi plus pi, and it's going to be repeated again and again. Now what I need to do here is to invert this thing here, this formula here, to find y of n, so I can just apply the formula. And the formula is the 1 over 2 pi, the integral from minus pi to plus pi, but here the signal is 0, or the y of ejw is 0, so all I have to do is integrate between negative pi by 4 and plus pi by 4, 1 over 1 minus e minus j omega, ej omega, and d omega. And then we've done this before, so but I'm gonna repeat it. So we've done something very similar to how to do this integral, and the trick is to replace this guy here by a sum, because a is less than 1. So basically what I did is I replaced this guy here by the corresponding sum, geometric sum. So this guy here is equal to sum from L equals 0 to infinity of, so this is going to be equal to a e minus j omega L, right? Because the first term is 1, and what you're multiplying again and again by the ratio is a e minus j omega. So that's what I did here. And then I can take the summation out and bring the integral in. And I have to work out this summation. Now to do this summation again, so we're at the stage where y of n is 1 over 2 pi, the sum from L equals 0 to infinity, the integral between minus pi by 4 and plus pi by 4, a of L e j omega n minus L d omega. And like we did last time, we need to distinguish between two cases, whether L equal to n or L is different from n. So again, so here n is fixed, so let me highlight it. So n is fixed and L is a running number, or a running variable, or running counter. So what I'm going to do inside this sum, I'm going to single out the case when L is equal to n. And now why you do this? Because if you try not to do it, you're going to see that the value of the integral is going to depend on whether n equal to L or not. So this is the case when, so even if you didn't notice this, when you try to solve the integral, you're going to see that it's going to become apparent, and you have to make this distinction. So again, n is fixed, think of n as 10, and n is running between 0 and infinity. So this is the case when L is equal to n, and in this case, this factor here, n minus L, is 0, so ej omega n minus L is 1, so this becomes the integral of AL, or AN, it's the same. The integral between minus pi by 4 and plus pi by 4, AN times 1 d omega. So this part is the easy part. And the remaining part, I have all the remaining sum minus that case. So that's why here I have to single out L equal to n. So this is the summation over all L different than n, and going from 0 to infinity. So this is going to become AL, and the integral of ej omega n minus L, it's exponential, so the integral is easy. So what you get here is 1 over j n minus L e minus j omega g omega n minus L. So you can see here that you have to divide by n minus L, and if n equal to L, you cannot do this. So like I said, so this case only exists if ej n minus L is not 1. So now if you do this, so you bring this guy here, so this is going to be equal to so an, you can take it out, and this integral is going to be equal to pi by 4 plus pi by 4, so pi by 2. So this is gonna be equal, so pi is gonna, so let me, maybe if I write it that'll be easier. So the integral here, so you're gonna take an outside, and this integral is gonna be equal to pi by 2, and then you're gonna simplify the pi, so you're gonna get an by 4. This is the part that is here. And now I continue to the other part of the integral, so it's the sum over L different from n, AL, and then I work out this part here, so it's going to be equal to this minus this, and then if I use Euler's formula, this is actually equal to 2j sine of pi by 4 n minus L. And then this is how you got 2 here, and the j cancels here. So again, let me write it down if I'm going too fast. So this is equal to 2j sine of pi by 4 n minus L. So this gives you the output of a low-pass filter to an exponential signal. Now let's look at the output for the second case where xn is sine pi by 2 times n and cosine pi by 8 times n. Now, so there is a typo here. So if you recall that then for the sine you have pi by j. So let me do this sine in let's say in blue. So there's a typo here. So the exponential or the DTFT of the sine function is actually pi by j, right? This guy here minus pi by j. So here I have to add the second sum from L equal to minus infinity to plus infinity delta omega plus pi by 2 minus 2 pi L. So if you remember, I did it last time. So sine looks something like this. So if this is 0, so you get pi by 2 here, and here negative pi by 2, and then here you're gonna get pi by j and minus pi by j, and then also it's gonna be repeated also again here, and so on and so forth. So we did last time the DTFT of the sine and cosine. So let me do the cosine also. Is missing the other part here, so I'm gonna do it in red. So here plus pi sum L equal minus infinity plus infinity delta omega plus pi by 8 minus 2 pi L. So the way to realize this, I mean, in the back of my mind, I'm just applying Euler's lemma or Euler's formula. I know that the cosine is ej omega n plus e minus j omega n divided by 2, and I know that and you should know that the DTFT of ej omega n is going to be a train of pulses at omega. Ej omega 0 n is a train of pulses at omega 0, and it's going to be repeated every 2 pi. So what is that telling me? This is telling me that the cosine and the sine and cosine are going to create specific frequencies, distinct frequencies in the frequency domain. Again, so this is to be fixed. Fix this. Now, what does that mean? This means that the cosine is gonna, or the sine is gonna create frequencies at pi by 2 and plus or minus multiple of 2 pi. So pi by 2, 5 pi by 2, 9 pi by 2. But remember that our cutoff frequency is by pi by 4. So, and this guy here, the frequencies are pi by 2 and negative pi by 2. So all these frequencies are gonna be cancelled and zeroed out by the low pass filter. So in some sense, the sine here has a high frequency, and it's not gonna go through the low pass filter. Now if you look at the cosine part, it has frequencies equal to pi by 8 and all its multiples, so actually it's within the low pass filter within the cutoff frequency of the low pass filter. So sorry, this is, I mean, here it's pi by 4. It's not up to scale, but it's more a conceptual graph. So here it's pi by 8. So this is how the cosine look like. So you have here pi by 8 and negative pi by 8, and also is repeated here and here. So this is, so the low pass filter is going to let the pi by 8 frequencies and all their multiples in or out of the filter, and this is why what's going to survive out of the filter are the low frequencies, which are pi by 8. Now if we take the last case, which is x of n equal to sine pi by 6n divided by n, so if you find x of ej omega here, then again, whenever you see this sinc kind of function, in the frequency domain, it's the low pass filter. So this is, the input is also a low pass filter at pi by 6. So it's the cutoff pi by 6, and your input has, or your system has cutoff frequency pi by 4. So this is so in the frequency domain, this is gonna look something like so. Again, so this is pi by 6 here. So it's all within your filter. So the whole system is gonna go through, in terms of frequencies, untouched, because also for our low pass filter here, the amplitude is pi. Actually, this is a typo. The amplitude is 1 here. If you go back to the given, so we're given that the amplitude of 1. So the frequencies in x of n are, all of them are gonna be outputted by the LTI system or the filter, and also they're not gonna be modulated, meaning their amplitude is gonna be the same. So the signal is gonna go through the LTI filter, the low pass filter, with no changes. So this is why the output is y of n is sine pi by 6n divided by n.